Hi, everyone. Thank you for the applause. I feel very good to be speaking to you today about the stuff that we're... So I'm going to tell you today about some of the things that we've been working on at Forethought. Forethought is a relatively new startup. Was founded in 2017. I'll tell you a bit about what we work on. The main mission statement is to empower everyone to be a genius at their job. And we try to do that by offering information retrieval embedded into employee workflows. That's kind of the one-sentence summary. And so the problem that we're trying to solve is that in the enterprise, employees need to access information to do their job all the time. It's estimated that 15 out of the 40 hours in the week, knowledge workers are spending that time searching for information to do their job. So that information can be contained in things like Google Drive, Dropbox, Slack, emails, depending on what you do for your enterprise. So what we've decided is to build these information retrieval tools, but to embed them inside the workflow so that you don't have to get used to using a new product or context switch from what you're working on. So obviously what that means is there has to be a different product for different types of employees. So the type of employee that we've started with is customer support agents. So these are people who answer customers' questions. A customer has a question for the company whose product they might be using. So the question comes in. It looks something like this. Kind of the lower half is the question. And as a support agent, I'm seeing this. And in this case, this is Zendesk, a very popular platform for customer support representatives. So what we've done is we've built an AI called Agatha Answers that can be installed through the Zendesk marketplace, also on Salesforce Front and a few others. But once it's installed, anytime that there's a question coming in from a customer, the customer support agent now has additional resources that they didn't have access to before. So in particular, they have this private comment in yellow that's supposed to be very small. It's very prime real estate. It's going to show up right there on the page in front of the agent, kind of in between the back and forth between the agent and the customer. And so it's very important there to not be too verbose with the information that we're showing. So one of our main problems is understanding the question and trying to answer it in 1 or 2 sentences. So we're not just trying to find a document that's relevant. We're also trying to actually understand what's going on and return 1 sentence. That's the yellow comment. On the right sidebar, we also have an app where we can show a bit more information, including some relevant docs. So this is kind of like Google search, where if you type in who is the 45th president of the United States, you'll get a card that says Donald Trump, maybe a bit of info, and then below that there's the lists that you're familiar with. So one thing in there, for example, is relevant videos, which is kind of cool, but all of this is actually done through text search. And so that's mainly what I'll be talking about today. So when you think about it, there's a few problems here. One of them is, how do you actually make sense of the question when you have potentially an email thread back and forth? I won't talk about that problem too much, except a bit at the end. The other problem is, how do you actually, let's say you have the question and you've extracted the question. In this case, it's basically, I'd like to match the events triggered by an anonymous user, blah, blah. So it's a 1-sentence long question. How do I take that and kind of compare it to every single document that I have in my database and run some sophisticated deep learning algorithms to get out some sort of ranking of which documents are the best, and also within the best document, find the actual answer. So that's what I'm talking about. There's 2 problems there. One, at least the way that we've done it, one is candidate selection. So obviously we can't run these deep learning algorithms in batch on millions of documents. which is potentially how large your knowledge base is. Knowledge base also includes all previous interactions with customers, so that's often millions of interactions. So that can't work. So the first step is to kind of conservatively apply a filter where we select a subset of documents where we make sure, hopefully, there's nothing that actually contains the answer that we've rejected through this selection. And then the next part, which is the part that's more interesting, is the scoring and the ranking using deep learning. So I'll quickly mention the first part. Basically, if you look at this at the left side of this, you have an incoming document containing a customer's question. We have a database which contains kind of the source of truth, all the previous documents ever, which are going to serve as the basis for our answer. And so what we have is Elasticsearch, very simple open source tool where we've implemented a few custom analyzers. So what that allows us to do is narrow it down from potentially millions of documents down to a few thousand, very conservative filter. And then from there, I'll talk about this question answering model, the arrow in the middle. And so just to talk about this very quickly, there's an incoming query which maybe has these terms in it. Those are terms that are maybe tokenized keywords inside the document, but it can also be synonyms of those words, maybe also the same words but with typos, so that you can account for typos, maybe one edit distance, something like that. That's going to be compared to this inverted index, and you'll find the documents that match. In this case, those two match because they have some of the same words. And the ranking of those, at least as far as Elasticsearch is concerned, depends on this kind of traditional NLP technique called TF-IDF, which stands for term frequency inverse document frequency. It's called this way because the score for a document given a term is the product of how many times that term occurs in the document. So if a term is, or let's say a word, is showing up many times inside this document, and this is a word that we've searched for, then you might think this is a good document to surface. On the other hand, if this word is very common, it really doesn't mean a lot if it's showing up very often. So for example, the word "the" is probably going to be in every single document. So the fact that it's repeated often in this document maybe doesn't mean as much. So that's why it's inversely proportional to the number of documents that the term shows up in. So this is all very basic stuff. And using that, we're able to filter down the candidate set to maybe thousands of documents. So from here, we've gotten to like the small problem of, given one document and a question, I want to return the answer that's contained in this document that answers this question, if there is one, along with a score for how good it is. And so I have a quick demo. So if I go somewhere on the internet and take a fact-based snippet of text and copy it. Sorry about that. And just paste this in here. So you can say, when was Oprah born? And you'll get back the one sentence that answers it, along with the actual answer highlighted. I hope you can see that. So you can ask a few more complicated things, like, what is her nickname? And you'll get back this sentence, and this is the nickname. Maybe one last one. What does Oprah do? And you get back this sentence with this answer. So this is a very trivial kind of example, but it's sort of the basic building block for what we're trying to do, which is, given a question, interpret what the question actually means semantically. So it's not keyword search. And then interpret all the documents that have been returned by our filtering operation, and try to kind of interpret the documents, the fact-based documents, in light of the question that you just saw, and yeah, just find the span of words inside the document that might contain an answer. So this is primarily what I'll be talking about, some of the basic building blocks that allow for this to happen, and then how some of the challenges that we've had with it and our ongoing research. So some necessary background. I hope I don't bore anyone with this. I'll kind of ask people as we go if I should talk about these in detail or not. But so these are some of the things that I'll talk about right now. The first thing, are people mostly familiar with Word2Vec? If you maybe raise your hand, if you are. Cool. So there's probably half of you who might like this, so I'll do this very quickly. One of the basic building blocks that we need is to be able to perform arithmetic on words or word representations. So in 2014, there was this nice paper by a person at Google who created this thing called Word2Vec. And so it stands for word to vector. And basically, the paper is representing words with vectors that are a few hundred dimensions, maybe. And these are, each dimension is some float, negative or positive. So in particular, kind of the canonical example that makes this nice is that if you take the vector that represents king and the vector that represents queen, and you subtract them, and you take the vector that represents man and woman, and you subtract those, you're going to get something that's almost parallel, which kind of means that semantically there's some notion of gender difference that's equivalent in both cases, as another example. But that's basically what it is. So it means you can apply functions on top of these vectors and obtain something that makes some semantic meaning. So now that we can do that, some functions that we can apply are neural networks. So in particular, for text-based problems, usually people work with recurrent neural networks, which are neural networks that kind of have an arrow back to themselves. And if you unfold it, it looks like that image on the right side. So the nice thing about these is that they're optimized for sequences. And so text, for example, is, let's say a sentence is a sequence of words. And in turn, if you wanted to take it even a step deeper, a word is a sequence of characters. So you can, you have this very deep neural network. Maybe you have 500 words in your paragraph. You're going to have potentially one layer for every single word, where at every step, once I've inputted a word, you have a vector that represents kind of the state that you're in now. And that vector depends on, it's a function of the word that you're seeing now and the previous accumulated state. And so there's some, here's a bit of the math. Basically, you start off with these words at the bottom, and now you have this E thing, which is the embedding space. So those are the potentially Word2Vec or glove pre-trained vectors. Instead of those, you could actually just have one-hot encoded vectors, basically all zeros except one indicating that this is the word in your vocabulary that you're talking about. And it would work as well, except that you would need a lot more data, because in addition to learning whatever you're trying to learn by using RNNs, you're also trying to learn the vocabulary and the meaning of words, which is a lot of work. And so starting from here, here's kind of some of the equations. I won't bore you with them, but so they're pretty important, because what we're saying at the end is that we're trying to obtain this output, which maybe is a softmax or some type of classification. We want to maybe say something about the input that we've just read. And so that's going to depend on your last hidden state, which in turn, if you unfold everything, depends on everything else. So that's pretty hard to train a model like this. Due to kind of the chain rule and backpropagation, you're going to have when you do the derivative of the last part, it's going to unwind, and everything you had from the beginning is probably going to lose its signal. This is called the vanishing gradient problem. You have these sigmoids at every step, and every time you're like squashing it into something close to zero, and you multiply many of these because you have many of these layers. And at some point, you're not going to be able to distinguish, is there any signal coming from here? Or there isn't any signal. Is it because there actually isn't anything here, or because the numbers are so small that it doesn't make sense anymore and I can't tell the difference? So you can't even fix that with just rectified linear units. So what people have done is use these things called GRUs and LSTMs. I can talk about these a little bit or not. Do people want me to talk about them? All right. Okay. So let's talk about one of them. GRUs, those are kind of more recent. So in addition to having your next state depend on the previous state and the word that's incoming now, you can have these two additional gates, one called the update gate and one called the reset gate, which if you look quickly at that last equation, the HT thing, the update gate is the ZT vector. So assuming that that's 1, you would get 1 minus ZT is 0, so all you're left with is HT minus 1. So that's a way of preserving the entire signal from your last hidden state. So if you do that every single time and you learn that if you have these word vectors or this hidden state, here's what the weights should be on these gates, then you're able to propagate that signal from the beginning to the end, which was something that we couldn't do before because of the vanishing gradient problem, but now we can. That's sort of what this stuff is for. And so now, instead of saying you have a layer or like an input or all of that, you'll just say I have this RNN with LSTMs, and that's kind of a basic building block, and you go from there. So in particular, all of this is useful for these sequence-to-sequence models, which for kind of a long time didn't exist, but around 4 years ago kind of started to exist. And in around 2016, they became the standard for question answering and for search. For translations also. So Google in 2016 switched from kind of rule-based translations to this stuff where you're not inputting kind of features based on deep expertise in linguistics. It's more I throw in a bunch of data and I let the model figure everything out. And so this uses two RNNs. There's one on the left side in red, and that one's called an encoder. And that's taking in an input. In this case, the problem is translation from French to English. But this is actually very generalizable. So for question answering, I'll talk about how you can also use this kind of architecture. But you have this RNN, let's say the left one, and the words are propagating through. You have hidden states, probably LSTMs or GRUs. At the end, you have one output from your encoder, which is this red thing, and that feeds into the decoder, which is the green thing, and there you're trying to kind of have the encoder encode all the information that you've seen into a vector representation, and then have the decoder take that vector representation and output something in the format that you want. So for example, if it's words in English, you'll start to consider, given that I've seen this last state from the encoder, and I'm seeing this word now, which is this start token telling me that I should start, I'm going to have a probability distribution over all words, or maybe a few concatenated tokens from my vocabulary, and you'll do softmax there, and you can compute a loss function and train it the same way that you would train any neural network. So that's kind of what happens there. could talk about this more if people want, but you can ask me if you do. So one problem with this, though, is that we're saying that at every step here in the hidden states of this green RNN, just like the RNNs that we saw before, my current state is going to depend on the previous state and the vector that I got back from the encoder, which is not really the way that humans work. That would be the same thing as saying, I need to translate this piece of text. So now I'm going to just read the whole thing, try to understand it. OK, done. I've memorized it. Now I'm going to translate the whole thing, because we're always just using this end representation. Humans don't really translate that way. They try to kind of translate it bit by bit at every step. They sort of know which area of the original text to focus on, and then apply the translation. So this is called attention. You're picking places to attend to. And this is also something that you learn. So this is another, depending on how you implement it, it's usually a two-layer neural network. So the way that looks is sort of like this. And this is actually really important. Attention is, at least right now, the way that models are differentiated. Everybody uses RNNs. Actually, they don't use that now. I'll say a bit about why, but everybody used to use these things, and so that's not where the power was coming from. It was more the data set and attention. So the attention works kind of like this. This is a bit of a different notation, but if you look on the right side, again, this is, you have your encoder, which is those squares above the x's. And then at the top, you have these S states. Those are from your decoder. And they're outputting an output, which is maybe a word. And so at every time that you're trying to output a word Y, that's going to depend on this new thing called attention. And so for the word that you want to output at position T, you're going to look at what is the attention between T and T prime. So that's a function of the state that you were in before, which is state of T minus 1, and presumably how much you should pay attention to every single other word that you saw in your encoder. And so you have this vector for each T in your output that you're trying to predict, and the vector tells you at this position how much you should pay attention to every single word in the input. So it's a function of those two things. Kind of intuitively, we know it has to be a function of them. There's a few different ways to learn this function. One way, when we don't know what a function looks like, that we can learn it is by applying neural networks. So two-layer neural network has a nonlinear activation in between. So we'll be able to learn something that's not linear. So that's usually what people do, and that's called additive attention. There's another kind which is called multiplicative attention, which we'll see a bit later. And that's sort of, you have a signal coming from a place, and that's represented by a vector. And then you have a signal coming from somewhere else, and that's another vector. If you do a dot product between them, you're kind of getting out the pieces that match are going to be amplified because they're getting multiplied. And the pieces that don't match kind of get depressed, and you're able to attend more to the places that match between those two vectors. So we'll see that just to kind of visualize what that looks like. So attention, again, if it's defined like this, it's a quadratic operation, because for every word in the output, you're comparing it to every word, or computing the attention to every word in the input. So it looks something like this. For some words, maybe you're attending to many things, because that's sort of how the differences in the language are. And yeah, so going back to the original problem, which was question answering, how does this all fit? Here's one paper from Salesforce Research about a year and a bit ago. This is not the best paper, but I think it's helpful to see kind of how we can reuse these building blocks. And so you have, this is again the problem that we saw with Oprah example. You have a document that contains a set of facts, and you have a question coming in maybe from a customer or just asking about a fact. And you're trying to output at the end two things, a start index and an end index of the span of words that's answering the question, if it exists. So one way to do that is to encode first the document that contains facts. That's an RNN with attention, or attention going to the end. We'll talk about that. And then same thing, encode the question. Now you have these two different things. You can concatenate them in a way that produces an encoding of the joined thing. And then you apply a decoder that uses attention. So we'll see a bit about of how that looks like. So you take this Q, which is kind of a matrix representing every vector at every state of the encoder for the question. Same thing for D, which is for the document of facts. You multiply them in one way, you multiply them in reverse in the other way, and then you concatenate those. They'll have the same dimensions. You concatenate them, and that gives you a representation of both of them. And actually, when you're multiplying, what you're doing is this multiplicative attention. So places that kind of match are going to be amplified because of the dot products. And if they don't match, then they'll get depressed relatively. And so this is why it's called co-attention. You're doing attention in both ways. The document is getting reinterpreted in light of the question, and the question is getting reinterpreted in light of the document. And it's a very interesting paper. At the end, you have, once you're done with the encoder, the decoder is kind of the same thing. You just have a pointer network at the end that's optimized to output these beginning and end indices. And then you can compute cross-entropy loss in the same way as you usually would. So now there's something more exciting, which is transformers. So people are saying, seems like this attention thing is very powerful because before that, we kind of had to rely on the last output of the last hidden state from the encoder. And now we don't need to do that, so why even bother with recurrence? And so these transformers are sort of the new thing. They're probably going to dominate everything, and they actually have started. So there was a paper about a year ago called Attention is All You Need by Google Research. And so that paper, I recommend reading it. It outlines this new construct called transformer. And there's no more, if you have an input of 500 words, it doesn't matter. You don't have 500 layers. And you can actually do some nice things with parallelization. And so you have your input. You kind of put all of that into a matrix. You can add some positional information, kind of concatenate that. And what you do here is you also apply an encoder and decoder, but sort of in a different way. So both the encoder and the decoder have two main sublayers in them. One is a two-layer feed-forward neural network, and the other one is this multi-head attention sublayer, which is taking the input as is, so this is a residual, and applying self-attention using this thing called multi-head attention, which I'll talk about. There's some scaling, etc. You get out this vector at the end, which goes into the decoder. Similar things happen there. You just have to make sure that you're not allowing it to attend to the words that it shouldn't be seeing yet. So that's why you have a masked multi-head attention there. But in the end, you just apply a linear transformation and a softmax, and you get out whatever it is that you want. So these are actually very generalizable and faster to train. So what this sort of looks like is they've now defined these three things: queries, keys, and values. And for our purposes, we can think of them as actually the same thing. You have input words, which are the queries and the keys and the values. And you're having the words do self-attention, like attending to each other in certain ways so that they all know about each other. So one way is this dot product attention, which we talked about. But they actually do this they repeat it many times. There's only one way that if you apply a dot product that words are going to interact, but that's why they apply h of these linear transformations into lower dimensional spaces through linear transformation with a weight vector, weight matrix W, and you get back these other vectors that are now able to, when you dot product them, interact in many different ways. Each one of those is a different matrix, and you're getting different interactions of the same words. And those are stacked, and then you concatenate them, you apply one last linear transformation, and you get out a vector. So this is really powerful, and actually there's this new paper now called BERT, which stands for Bidirectional Encoding Representations from Transformers, which I highly recommend reading. Basically going to revolutionize everything. This came out 3 weeks ago, and so that's sort of something that that is actually pre-trained on the English language and is able to be reused on sort of any text understanding problem that you have, including question answering. And so now really it's all about having a good data set, unique data set for your problem that is specific and that you can train on. One additional layer, just transfer all the learnings you know about English to this one problem that you have, and you're done. So I think I'm running out of time. I'd like to open it up to questions. One last thing I'll say, we're hiring at Forethought for machine learning, backend. We recently won at TechCrunch Disrupt SF, which was really cool. And please reach out to me if you're interested. We have many different, the question was, what was our training data? We had many different training data sets. At first, we needed to bootstrap, so we used a lot of open source things out there, like Apache bugs and Jira bugs. Started with those. There's also data sets for general question understanding, question matching, question answering, text understanding. So we trained on all of those to bootstrap. And now we actually have a few really good customers, so we have a lot of data from them, and we now have a much more specific data set for customer support, which is the problem that we're trying to solve. Yes?
How do you measure the answer is correct?
So the question was, how do you measure if the answer was correct or not? During training, it's easy because you have labeled examples. So if that's what you're asking about, there's F1 measures of kind of how many words you returned should have been in the answer and how many did you miss, that sort of thing. In the real world, how do you measure if you're improving the performance of support agents? That's a little bit trickier. There's a few ways. One is explicit signals from the agents when they click the button to apply the answer that we gave them. That means there was something right. In addition, there's implicit feedback, which is comparing sort of like an edit distance between the answer that we left and the answer that the agents ended up using. So that also informs us on how we're doing.
How do you do the ranking?
The question was, how do we do the ranking? And that's a great question. We're still sort of figuring that out. There's a few different ways. One kind of trivial way is have good discriminative features and sort of use maybe a neural network or a random forest to be able to predict given features what is this score, and then sort in descending order by score. That's one way. Another way is with kind of learning to rank techniques, more like pairwise comparisons or list-wise comparisons. And yeah, that's what we're doing now.
So what if it's unsupervised? So this seems to be a semi-supervised method.
I'm actually, sorry, the question was, this seems like a semi-supervised method. If we had a training data set where it wasn't a supervised problem, how would we apply this learning to rank? I'm actually not sure. I would have to research that. Part of our problem now is getting people to use the product in ways that we can explicitly determine labels so that we can do supervised learning.
One last question. How does it work with different languages?
Yeah, good question. The question was, how does it work with different languages? And so there's many components in the algorithm. A lot of them will work across language. It just depends on the corpus of text that we're using. But some of the secret sauce will only work for English right now because the models that we've pre-trained on were specifically for English. It would take some effort and probably people who speak other languages to do it in other languages, but there's kind of no fundamental reason why we couldn't. But yeah, good question. Yes?
Yeah, I'm curious, so when it's sort of deployed in production, how do you
Yeah, good question. The question was if you have business-specific terms in the knowledge base, but the customer is asking a question and not using the correct terms, how do you still understand? So one way is that we're not generating these answers ourselves. We're trying to match to existing answers for existing questions, which might be very, very similar. So as long as you can match the incoming question to a previous question, even if the answer has sort of different language, you've learned that this language is appropriate as an appropriate answer to that question, and you can return it.
So you mentioned that you did not generate a new answer. You just started the previous answer.
Yeah. The question was, we return existing answers. We don't generate new answers to new questions. How would we do if there's a new question that's never been seen before? Right now, we wouldn't do well on those. It's actually never happened that there's a question that does not have an answer in any way. It almost never happens. You'd be surprised how redundant questions are, even if it's not redundant enough to warrant a template response. When you have millions of interactions, it's very unlikely that you'll have something for which you can't return anything useful. In those cases, those are maybe a drop in the bucket. We try to measure our impact at the end of the day overall on the ticket resolution times, customer wait times, and that really hasn't been an issue so far.
No, I just want to comment. Actually, not your company, but the other some famous AI company.
Not sure. Sorry, could you repeat the last part?
I mean, it seems, I'm not sure, but it seems they are case system.
Okay, you're saying that there's some solutions that return templates when it's not what you're looking for. Yeah, I know about those. We try not to do that. There's a world in which we're smart enough to abstractively generate the answers. That's kind of trickier and riskier, and also potentially doesn't extend well across customers. We would train something very specific for someone where it's not learning to match to existing questions, more like understanding very deeply the knowledge that exists there, which is different from the knowledge in another customer's corpus.
So you showed an example where you took a paragraph and asked a question.
Yeah, good question. The question was, I showed an example of Oprah. When was Oprah born? I got back the span that contained the date. Can it answer how old is Oprah? Yes, it will answer how old is Oprah, but it will do the same thing, which is highlight the date that she was born. So it doesn't generate free-form text.
It cannot take today's date and
No, that would be kind of fundamentally different. We could certainly add rule-based hacks, sort of, because people ask about dates often, and it would be easy to detect, but right now we don't have that. We would instead return the span that contains the answer semantically, and you would have to generate it yourself. Yeah, the question was, I mentioned GRUs and LSTMs. Yesterday someone was talking about bidirectional GRUs and LSTMs. Is that new? Is it something we use? It's not new. I actually forgot to mention that. I think in one of the slides it was bidirectional. That means taking in the signal from the previous words in the input and the next words. And actually the last model that I mentioned, BERT, bidirectional, it's not LSTMs or GRUs, but this bidirectionality is part of why it's able to perform much better than existing solutions. There's kind of engineering problems there because with that model, it's not as simple as it is with GRUs of saying just take this and take that, because you get cycles. Each here will refer to the word, and then next will refer to the same word, then the word is kind of referring to itself. So instead they try to randomize and randomly mask the word and things like that. Bidirectionality is important to be concise. Right. Got it. So yeah, that's a good question. So certain languages, the meaning is contained at the very end instead of the beginning, and if you had bidirectional, maybe that would help you. Actually, it doesn't really matter which direction you're going, if you went left to right or right to left, as long as you're consistent, because the model is just going to learn, I should attend to the beginning or not. But bidirectionality means you have both, which is more information.
Okay, thank you guys for all your questions. If you have any more questions, please ask Sami after. And Sami, thank you for a brilliant talk, and let's applause.
Thank you. Thank you.